Hello everyone, welcome to this lecture on application specific integrated circuits, commonly known as ASIC, and its impact on embedded systems. ASIC is one of the most important technologies used in modern electronic design, especially in application that requires high performance, low power consumption, and compact size. In today's world, almost every electronic devices we use relies on embedded systems. Devices such as smartphone, then smartwatches, medical equipment, automated control systems, and Internet of Things devices, and all are depends on the embedded hardware to perform specific functions. As technology continues to advance, there is an increasing demand for systems that are faster, more efficient, and more reliable. To meet these requirements, ASIC technology is widely used because it allows engineers to design hardware that is optimized for a particular application. Unlike general purpose processor, ASICs are designed to perform dedicated tasks with maximum efficiency. So this results in faster processing speed, reduced power consumption, and improved overall system performance. So ASIC also help to reduce the size of electronic systems by integrating multiple components into a single chip. So in this lecture, we will explore the fundamental concept of ASIC technology, and we will discuss what ASIC is and how it differs from microcontrollers and FPGAs and the step-by-step ASIC design flow we will discuss, and we will also examine the ASIC architecture and its advantages and limitation and its real-world application in industries such as consumer electronics, automotive, medical, and IoT. By end of this session, we will have a clear and comprehensive understanding of ASIC technology, its importance in embedded systems, and how it plays a crucial role in shaping modern electronic devices and future innovation. Now, coming to the next slide, introduction to ASIC. So, what is ASIC? ASIC stands for application specific integrated circuit. You can see I have shown two diagram. One is real physical structure before after fabrication in the right hand side, and left hand side is the before before fabrication of the integrated circuit, which is known as layout of that circuit. And it is a semiconductor chip designed and manufactured to perform a specific function to our application, unlike general purpose processors such as microcontrollers or CPUs, which are designed to handle a wide range of tasks. And ASIC is optimized for a single dedicated operation. This specialization allows ASICs to achieve higher performance, lower power consumption, and greater efficiency compared to the general purpose devices, because the hardware is customized for a particular task. So ASIC actually eliminates the unnecessary components and focus on only required functionalities. Means it is a customized chip. So ASICs are widely used in modern electronic systems where speed, efficiency, and compact size are critical. Some common example includes mobile processor, which are designed specifically for smartphones to handle communication, graphics, and signal processing efficiently. And another example is cryptocurrency mining chips, which are optimized to perform complex mathematical calculation which is required for blockchain mining. So, the signal processing chip, which is used in communication system, audio devices, and image processing applications, are also ASICs. In addition, automotive controllers such as engine control units and uses ASICs to manage the vehicle functions reliably and efficiently. The key concept behind ASIC is specialization. General purpose processor can perform multiple tasks but may not be highly efficient for any single task. In contrast, uh, an ASIC uh, an ASIC is designed to perform one specific task with maximum efficiency and speed. So this makes ASICs ideal for embedded systems that require dedicated functionality. A simple analogy can help explain this concept. An ASIC is like a custom built machine designed for one specific job, such as a machine that only produces screws. It performs that job very quickly and efficiently. On the other hand, a microcontroller is like a multi-purpose machine capable of performing different tasks, but not a faster or efficient as specialized machine. Now, coming to the next slide, the comparison of ASIC, microcontroller, and FPGA. So, microcontroller, FPGA, and ASICs are three important hardware technologies widely used in embedded systems. Each has unique characteristics, advantages, and limitations depending on the application requirements. Understanding their difference helps engineers to select the most suitable technology for performance, flexibility, then power efficiency, and cost. So, a microcontroller is a general purpose programmable device designed to perform multiple tasks. It offers high flexibility because its functionality can be changed easily through the software programming. So microcontroller can operate at medium speed, which is sufficient for many embedded applications such as home appliances, industrial control, and IoT devices. Their power consumption is moderate, making them suitable for battery powered system. One major advantage of microcontrollers is their low development cost and low per chip cost, making them ideal for low volume and cost sensitive applications. And FPGA provides a very high flexibility as its hardware can be reconfigured even after manufacturing. So engineers can design custom digital circuits inside an FPGA using hardware description language like Verilog or VHDL. So FPGA offers high-speed performance, which is greater than microcontroller but slightly lower than ASICs. However, the FPGAs generally have high power consumption due to their programmable nature. The development cost is medium and the chip cost is also moderate, making them suitable for prototyping, research, and applications requiring hardware customization. And ASIC is designed for a specific application and cannot be modified after fabrication. Therefore, its flexibility is very low, but it provides very high speed and extremely low power consumption because the hardware is optimized for one task. Although the development cost is very high and cost per chip becomes very low in mass production, making ASIC ideal for large-scale products such as smartphone, automotive controller, and AI processor. So, in summary, I can say that the microcontroller are the best for flexible and low-cost application compared with the FPGAs are ideal for customizable hardware design, and ASIC provides the highest performance and efficiency for dedicated application. Now coming to the ASIC design flow. This is one of the important part area in ASIC design process. So the ASIC design flow is a systematic and structured process used to design, develop, and manufacture a custom integrated circuit for a specific applications. So this process ensures that the chip meets performance, power, area, and functionality requirements. The ASIC design flow consists of several important steps, starting from defining requirements and ending with chip testing. The first step is specification. The first stage in ASIC design is the specification stage. In this step, the overall requirements of the ASIC are clearly defined, and this includes determining the functionality of the chip, the expected speed of operation, and power consumption limits, chip size, and interface requirements. For example, if the ASIC is designed for a mobile processor, it must support fast data processing while consuming low power. The specification documents acts as a blueprint and guides all the further design stages, or if any errors arise in this stage can affect the entire design process. So it must be carefully need to be prepared. So this is very essential stages in design life cycle. So the specification is the very important steps. Now coming to the next step, which is known as RTL design. So the next stage is it's very important RTL design steps. So in these steps, the functionality of the ASIC is described using hardware description language such as Verilog and VHDL programming. VHDL stands for Very High Speed Integrated Circuit Hardware Description Language. So designer basically write the code to represent the logical behavior of the circuit, including data flow, then control logic, then processing different operations. And RTL design describes how data moves between registers and how the system performs its intended operations. So this stage converts the design concept into digital logic representation that can be simulated and verified. Now coming to the step number 3, that is called functional verification. So functional verification ensures the RTL design workflow correctly according to the specification. So in this stage, simulation tools are used to test the design with different input conditions. That is known as test benches. So different test benches are created to apply input and to verify the output. For example, suppose if I want to design one NAND gate, so we know the truth table of the NAND gate, we know the input and we know the output. So by using the input test bench like two input NAND gate, if we'll apply 0 0 1 0 1 1 0 and 1 bit pattern, then we already know what are the expected output. If there is any deviation in that output, then that we need to verify that particular functions, which is known as functional verification. So this helps to identify the design error or logical bugs before moving to the actual hardware implementation. So functional verification is very important because it fixing the bugs at the later stage it can be very expensive. So at the early stage, if we able to detect the or will able to detect the bugs, or if we'll able to fixing the errors, then at the later stage we can reduce the cost as well as time also. Now coming to the next steps, that is called synthesis. This is very important steps in our art ASIC design flow. So as per the Y chart, which is proposed by D. Gajaski, so there are three different domains. If you see, there are three arrows. So first right top at the right hand side arrow is known as behavioral domain, and the top left side domain is called uh, structural domain, and bottom one single arrow is known as geometrical domain. So three domains are there. So when we are writing some code in the at the in this synthesis stage, what are the code we have written in the RTL is converted into gate level representation. So this process uses different synthesis tools to translate the hardware description code into logic gate, such as different logic gates like NAND gate, NOR gate, which is called this NAND NOR, not and or XOR XNOR. These are called micro cell, and some mega cell also available in the standard cell library. It's like a flip flop, different types of flip flop, SRJK, then register counter. Then these are the sequential circuits. Similarly for some combinational circuits like half adder, full adder, this kind of circuits are called macro cell. Also be possible to convert from behavior or from RTL. It is called RTL code is nothing but it is called behavioral representation of the circuit. To by using the synthesis tool, we can convert into structure, real structure of the logic gates, or mega cell, micro cell or mega cell. Micro cell means logic gates, and mega cell means combination of multiple gates. We are able to design different types of subsystem. So these are called microcell. So this synthesis tool also optimize the design to meet timing, power, and area constraint. The output of this stage is called gate level netlist, which represent the circuits in terms of standard logic cells. And similar like our C programming in C or C++, when we are writing some code, and the first step is to save that particular code, and after that we need to compile to check whether there is any error or not. If there is any error, it will generate an error list, compilation error. If there is no compilation error, then we can run that code. Similarly here, synthesis and compilation both are same, basically used for check the RTL code whether if the code is correct. So synthesis tool will generate the error report. If there is any error in the RTL code, then it will generate one error report. If there is no error, automatically it will convert into structure. So this is the basic function of synthesis process, and this is very complex, not so easy task, because it is changing from one domain to another domain, so it is very challenging. So this particular synthesis tool are very sophisticated and very advanced. Now coming to the physical design, so that is step number 5. So physical design basically converts the gate level netlist into physical layout that can be manufactured. So this stage includes several important steps such as floor planning, placement, routing. So, so floor planning actually defines the overall layout and placement of major blocks on the chip. Placement mainly basically used to place all the different modules and sub module in a particular major blocks on the chip. And placement actually determines the exact location of the individual logic cell where need to place. Okay, so another important uh, physical design process is called routing connection routing. So the function of routing basically used to connect all the components which we already placed, different cell or different blocks are placed, need to be connected using metal interconnection, metal connector, using copper, aluminum, gold, different of conducting material we can use based on the requirement of the circuit. So this stage ensures that the chip meets the performance and timing requirement while minimizing the area and the power consumption. Now, the coming to the next step, which is called the fabrication. So once the physical layout is complete, the design is sent for fabrication. So fabrication is the process of manufacturing the ASIC chips in semiconductor fabrication facilities. So the layout data is used to create the masks, and the chip is manufactured using silicon wafer processing techniques. So this step converts the design into a physical silicon chip. Now coming to the testing part, the final stage is known as testing. After fabrication, the chip is tested to ensure it functions correctly and meets the design specification. So various test techniques are used to verify the performance, then functionality and reliability of the circuit. So the testing actually helps to identify the manufacturing defects and ensure the chip works properly in real world applications or not. So once testing is complete, the ASIC is ready to develop for development stage in embedded systems or any electronic devices. Now coming to the next slide, that is known as ASIC architecture. So ASIC architecture refers to the internal structure and organization of an application-specific integrated circuit that is designed to perform a specific function with high efficiency and speed and reliability. The architecture actually defines how the different components within the chip are arranged and interconnected to achieve the desired functionality. Since the ASICs are developed for a dedicated applications, their architecture is optimized to deliver maximum performance while minimizing the power consumption and chip area. So one of the major component of ASIC architecture is the processing core. So this is the central unit responsible for performing the main computational operations such as arithmetic calculations, then logical operations, and data processing. So the processing code executes the instruction required for the specific applications, making it the most important functional blocks of the ASIC. Another essential component is memory, which is used to store data, program instruction, and intermediate processing results. So here memory actually allows the ASICs to access required information quickly and efficiently, improving the overall speed of and the performance of the system. So different types of memory, such as RAM, then ROM or cache memory may be integrated depending on the application requirement. Then the input and output interface is also one essential elements or essential component in ASIC architecture. So this I/O interfaces actually enables the communication between the ASIC and external devices such as sensor, actuator, microcontroller, or other system components, which is required for real world application. It ensures proper data transfer between the ASIC and the external environment. So the control units is fully responsible for managing and coordinating all the internal operations of the ASIC. It controls the sequence of operations, manages the data flow, and ensure that each component works correctly in synchronization. So this is the feature of uh, I/O. Now coming to the clock system. See, the clock system is another critical component that provides the timing signals to all parts of the ASIC. So this timing signal ensures that operation occurred in a synchronized manner, maintaining the accuracy and reliability. So clock synchronization is very essential for that. We need one clock system. Sometimes we are using clock distribution network for high-end ASIC application. Now, the ASIC can be classified into different types of based on their design approach, which is known as full custom ASIC. Uh, mm, the full custom ASIC is completely designed from the transistor level, or we can say to design from the scratch. Okay, so this is called full custom ASIC, which it offers the maximum performance, then lowest power consumption and the smallest chip size, but it requires high development time and cost. So, and whereas in semi-custom ASIC used pre-designed some standard cells, which reduced the design time and cost while maintaining good performance. So a programmable ASIC allows a limited configuration after manufacturing, providing some flexibility. And a system on chip is an advanced type of ASIC that integrates processor, memory, input-output interfaces, and other components into a single chip, so creating a complete embedded system solution. Now, coming to the next slide, that is the impact of ASIC in embedded system. Here you can see I have shown few sample of application specific integrated circuit, which is in real world application we are using in different devices, and this ASIC is now applicable everywhere in wireless communication technology, then air defense system, satellite communication, navigation, then radar system, then our personal computer, then embedded devices, IoT enabled devices, AI enabled, AI accelerated processor design. So everywhere it is useful. So in this slide, I will cover the impact of ASIC. So this ASIC have significantly transformed the design and performance of modern embedded systems. So embedded systems are used in wide range of applications, such as just now I told the smartphone, in medical devices, the automotive system, consumer electronics, and IoT devices. These systems require high performance, low power consumption, then compact size and reliable operations. So ASIC technology has made it possible to achieve these requirements by providing hardware that is specifically optimized for a particular functions. Unlike general purpose processor, ASICs are designed for a dedicated task, which improves overall system efficiency and effectiveness. So one of the major impact of ASIC in embedded system is reduced power consumption. Since the ASICs are designed for a specific application, they eliminate the unnecessary circuitry and operate more efficiently. So this results in significantly lower power usage compared to microcontroller or general purpose processor. For example, smartwatches uses ASIC chip that consume very little power, allowing the device to operate for several days on single battery charge. So this makes ASIC ideal for battery powered and portable devices. Another important impact is high speed processing. So ASIC actually provides much faster performance because they are optimized for specific operations, unlike microcontrollers that perform multiple tasks. So here ASIC actually focuses on one dedicated function which increase the processing speed. For instance, video processing chip used in smartphone and camera are ASICs that can process high resolution video in real time without any delay. So this enables smooth video recording and streaming and image processing. And ASIC also contribute to smaller system size by integrating multiple components into a single chip. So ASIC reduce the need for additional external hardware. So this helps in designing compact and lightweight embedded systems. So mobile phones are the good example where ASIC technology allows powerful processing capabilities within a small and portable devices. And another key benefits is high reliability. Since the ASICs are designed and optimized for a specific function, they operate with greater stability and fewer errors. This reduces the chances of system failure and improves overall reliability. So, ASICs are widely used in critical applications such as automotive control system, medical devices, where reliable performance is very much essential. And finally, ASIC provides better overall performance. It optimizes the hardware, ensures efficient operation and faster execution and low power consumption. So this improves the efficiency and lifespan of the embedded system or embedded devices. So overall, ASIC technology plays a crucial role in enhancing the performance, efficiency, and reliability of modern embedded systems. Now coming to the next slide on real world application. So I'm going to discuss here. So mainly ASICs are widely used in many real world applications due to their high performance and low power consumption, then compact size and reliability. They play a critical role in improving the efficiency and functionality of modern embedded system across various industries and mainly in consumer electronics. ASICs are commonly used in mobile processor. For example, the Snapdragon processor now most of the mobile smartphone we are using. So each and every processor having that kind of tiny kind of processor which is a application specific processor and the integrated circuit also named as application specific integrated circuit which is frequently used in such kind of smartphone and this Snapdragon processor which is used in smartphone is an ASIC design specifically for mainly it is for mobile applications and it efficiently handles tasks such as communication, then image processing, then video playback and power management. So this enables smartphone to deliver high performance while maintaining low battery consumptions. In automotive system also it is very much useful. So ASICs are used in important components such as engine control unit and advanced driver assistance system. Now everybody most of the companies are using ADAS technology. So this is also here it is useful. And the ECU uses the ASIC to monitor and control the engine parameter like fuel injection, then ignition timing, then emissions. And the ADAS system use ASIC for the functions such as collision detection, then lane monitoring, then parking without any distraction. Uh, then automatic braking systems also there. Then real time accident, if any accident will happen, automatically airbag system will open such kind of vehicle safety purpose. This particular IC is very useful. In medical devices also ASICs are used in equipment such as ECG machines and glucose monitoring. This ASICs ensure the accurate signal processing, low power consumption and reliable operation which is essential for patient monitoring and diagnosis. In IoT devices, ASICs are used in smartwatches and smart sensors. So this device requires compact size, low power consumption, and efficient performance with ASIC technology provides effectively. Coming to the next slide is the advantages and limitation and future trends. So this ASIC offers several advantages that makes them highly suitable for modern embedded systems and high performance applications. So one of the most significant advantages of ASIC is very high speed since the hardware is designed specifically for a single application. So all unnecessary logic is removed, allowing the circuit to execute operation much faster than general purpose processor or microcontroller. So this makes ASIC ideal for application such as video processing and communication system and in latest AI technology also. Another major advantage is low power consumption. So ASIC consume very significantly very less power because they are optimized for a specific task. So this is especially important for battery powered devices such as smartphones, smartwatches, IoT sensors, where energy efficiency directly affect the device lifetime. So ASICs offer small physical size as multiple system component can be integrated into single chip. So this enables compact product designs and reduces the overall system complexity. Additionally, ASIC provide the high reliability because they are dedicated to one function and operate with stable and predictable behavior, making them more suitable for safety critical system like automotive and medical devices. Despite these advantages, ASIC has some limitation. So one of the main drawback in this high development cost is very important. So designing an ASIC requires specialized tools, then skill, manpower, then it is very expensive for fabrication process, need a proper foundry, making it costly compared to the microcontroller or FPGA. Another limitation is ASIC cannot be modified after fabrication. So once the chip is fabricated, after that we cannot alter. That is the biggest drawback in ASIC. So once the chip is manufactured, it functional is fixed, and any design error may require redesigning the entire chip. So this is very challenging. So we need to ensure whether each and every from the scratch, each and every step must be validated. So as it also involve long development time. The time it will take very big time as the design, verification, fabrication, testing process are very complex and it is a time consuming process. So looking ahead, the ASIC technology continues to evolve with emerging applications in AI. ASIC chips are being developed to accelerate the machine learning and deep learning tasks efficiently. Then in edge computing, ASIC enable fast data processing near the data source, reducing latency and power usage. So automotive ASIC supports advanced driver assistance system and automotive autonomous driving. In biomedical, ASICs are increasingly used in medical imaging, then wearable health monitoring and implantable devices. A well-known example of AI ASIC is Google TPU, which is specifically designed to accelerate machine learning workloads overall. Despite their limitation, ASIC remain a key technology shaping the future of high performance and energy efficient embedded system. Now, coming to the conclusion, in conclusion, I can say that the application-specific integrated circuit play a vital role in the advancement of modern embedded systems. They provide exceptional performance, low power consumption, compact size, and high reliability, which are essential requirements for today's electronic devices. Unlike general purpose processors such as microcontroller and CPUs, ASICs are specifically designed and optimized for a dedicated application. So this specialization allows ASICs to operate more efficiently, perform faster, and consume less energy. So ASICs are widely used in various applications, including smartphone, medical devices, automotive control system, and IoT devices. In smartphones, ASIC enable fast communication, image processing, and efficient power management. In medical devices, they ensure accurate monitoring, reliable performance. In automotive system, ASIC supports engine control, safety features, and advanced driver assistance system. Similarly, IoT devices benefits from ASICs due to their compact size and low power operation and small area. Although ASIC development involves high initial cost and long designing time, the long-term benefit is performance and efficiency and reliability make them essential for large-scale and advanced application. With the rapid growth of artificial intelligence, Internet of Things, wearable devices, and smart technologies, ASICs will continue to play a key role in shaping the future of embedded systems. Thank you very much.